Okay, let's get back to business. This lecture 8 also. Suppose that will be recorded. Do you want me to continue for formal lectures or not? No, that's fine. I will. But you won't be. You will leave next week.
I don't know yet.
It's easy for you
it's
to.
It's not guaranteed, but I will watch anyway.
Okay.
I will support from afar.
Yeah, I should just make it a private vlog, yes, community vlog, without.
I'm telling you, you should stream it.
Okay. So
on TikTok.
What I will do today is we do asymptotic study of VA Fock solution. So I suppose you don't remember what we did last time. Since it's a continuation of previous lecture, and I think it happens, it happened before. But usually I try to cover a single piece in one lecture. So here I want to study the solution, so then I will get back to problem treatment. So what we had? We had cylinder. Then we had green lane coming, propagating towards the cylinder. Then we had some weird coordinates. We had a coordinates going along the surface of the cylinder. We call it lateral coordinate. And we had radial coordinates. And what else do we need to know about this cylinder? It has its radius is r. We can introduce polar angle phi, and for completeness we also have usual polar coordinate r. And then in our new coordinate system we have L is equal to r phi, and h is just this difference, r minus the radius of the cylinder. Good. Then we solve this problem using Fourier transform method. And before we solve it, we introduced dimensionless coordinates. Coordinate tau, which goes along the surface. It's good if you will at least remember during the lecture that tau goes along the surface and eta the second one is orthogonal. Because I will do some physical analysis. So we move to these coordinates to get rid from additional constants. And in these coordinates our harmonic equation looks very nice. total field is the sum of the incident wave and scattered field, and incident wave looks like this. That's all we did last time. And after a lot of efforts and some study of area equation, we came up with the Fock solution of this problem. And you remember AI as a solution is like a usual area function, and this is, it's called the Fock function, a modified area function. It's a solution to area equation which behaves as an outgoing wave at infinity, so it has like an exponent and some decayed factor, the first order of it. Okay, we have this solution, and now we want to analyze this solution, because we did a lot of things and we just want to make sure whether these things indeed behave as a scattered wave, whether it has a reflected wave, whether it has like a shadow. And before we come to analytic study, we should do, and this is probably the obvious step if everybody wants to solve problems, diffraction problems. Here, first need to have a rough physical understanding. And the simplest thing we can do from a physical point of view is to do some ray analysis. And ray analysis, is much simpler than it sounds. So we have a wave coming onto the surface, and if we just follow a usual rule of like the angle of incidence are equal to the angle of reflection, each such wave should generate a reflected wave. And then we have a critical ray which touches, which tangent to our circle cylinder. And this ray goes just straight forward. It doesn't, of course, there is some diffraction happens here, so we have some complicated diffraction field here, but for geometrical theory we don't have anything, so we don't have a reflected wave. And so here we have our last reflected wave. But this line, I'll draw it with another color. This line is known as light shadow boundary. If it's light, if it's light. So here we should have our field should be small, and this field should not contain any or incident wave, the total field. And probably, so here scattered field should somehow cancel the incident field, because our field is a sum of this term plus this term, so a sum of these two terms should be approximately 0. So this is the first thing we are going to check. But because we already got into dimensions as coordinates, our coordinate system is curved, I probably first should show you how this line looks in coordinates eta tau. And so this ray is just y equal to 0. If I put it depends where, of course, I put 0. If I put 0 here, then it's y equal to I. And anyway, in my new coordinate system, this thing will go to that will be a parabola. Yeah, makes sense. That's a parabolic equation, and from straight lines we go to parabolas. And of course, you can just check through this change of variables that straight line is eta equal to tau squared. Should look more or less believable. I need derivation because it's trivial. Is it fine? You are not concerned with this. Okay. So you just at this point, and again, I should. As this is will be the light zone, and this is what's called I illuminated zone, and this is shadow. So what we want to show today, part of our question, is that below this line, when tau square is bigger than eta, we have field which is approximately 0, asymptotic. Okay. Well, I have homework for you, if you wish. So homework, implement this formula in MATLAB, implement in MATLAB. And in MATLAB, you have these functions built in. For this function, you also know because it's AI plus AI bi. So for this function in MATLAB, you can use this thing, and it should compute very well, at least in some areas. And I estimate that in MATLAB it will be like 10 lines of code, because there is like nothing too complicated here. And check that you get this type of result. So this area like this. Yeah, illuminated, and here you have almost 0 numerical. So it's like, if you for some reason have square 10, that's a fun thing to do. And okay. Then, of course, to analyze this integral, we will use saddle point method, which makes sense. We have an exponential term, and we have some function. Of course, this function is this thing is quite complicated, because it's a special function. It's also some integral, you remember, like x e tau cube plus something. So this thing also can grow or decay, or it can have zeros. And we will discuss these things in more details later. Okay, I remove this part. And since we are not very well mathematically educated, so this will be point B, previous one was point A, we will use so-called fake saddle point method. It's fake. I will not justify it mathematically in a rigorous way, but I think that it's simple and it works. And if you want to, of course, to find a correct way, I refer you to like more or less any complex analysis book or to theory of ordinary differential equations, to, for example, Frank Olver's book mentioned a bit later today. But anyway, on practice, when we just try to do some estimates, we can do the following thing. So we have the following integral of the structure. This function is supposed to be analytic, at least in the domain where we have several points. And we have some phase function, which is here in red line. And the difference that for normal, for rigorous saddle point method, you also need to have like big parameter, like for example, alpha, lambda, big parameter. And here I will avoid this part. I will say, doesn't matter, let's just think as we have this parameter, and I won't be getting in details, because when we have a big parameter, this thing oscillates very fast. All contribution to the integral, they cancels almost everywhere except the stationary phase point or saddle point, depends on how you refer to it. And here I say, anyway, when it's not big, it still oscillates, and we can deform our contour of integration, and we can make the integrand exponentially small apart from the saddle point. So it's still a special point. And let's see whether we can do it. So, but the things I will do are very algorithmic. So we're looking for points, saddle points, tau star zeta on real axis. So we only look for points on real axis. So these points, they definitely will provide some wave terms because they will give us an oscillated exponent. And if the point has some imaginary part, it will lead to exponentially decaying waves. And you have points like this, and they are found from this condition. And slight justification to this idea is follows from the following picture. I don't know whether it will help you or not. And we have our contour. I will draw it slightly above, but I think it's on the real axis. And we have our saddle point. And then the same thing that I said right away. We have in mind the following deformation. Depends, of course. We can deform this way or another way. It depends how a function grows and decay. But we have this type of a deformation in mind. And around here, since we deform, our I integral will decay here and here, but will be quite big around this point. So this is the idea, but just for now we forget about this point. And if we were able to find this point and justify something like this, we can say, okay, we are probably asymptotically, our field behaves like this. And here I have plus minus. Of course, this plus minus linked with how I deform my contour, like this or like this. Then I will have two different pose on type integrals. Here, like a usual idea of saddle point method, I just leave the quadratic term, and quadratic term, I the exponent will lead to similar result. So, but I tried to write this formula in a form that you can use it right away. So the only thing I should clarify that you use plus for positive and G double prime means a second derivative at this point. I should write it like this. Minus a negative. Okay, now we have this formula. Let's try to apply it. Our first example will be quite simple. That will be a plane wave. So now I will obtain some trivial results. Is it okay so far? Is it follow? Do you think you, Gabriel, can use this formula later? Is it like I am familiar with this one? Yeah, I did in precisely this one. So I saved a bit of algebra if you forgot the coefficients. So flexible point method for plane wave. I will right now write down a Fourier decomposition for plane wave. We will have a simple integral to estimate. So, let's apply Fourier transform. Oh, I just applied Fourier transform to plane wave. You recognize this function. Yeah, I need to say you are not allowed to not recognize this function. And give you one more chance. Yes. What? No, that's any function. But that's how we have it. So we have a third order of is it we have a third order of so tau. It's not I can think that that's one the tau. So now the variable of integration is tau and tau cube. So this is how it's in the function, but that's what it is. Otherwise it doesn't. Okay, good. And then we can reverse transform and we have the following representation, the integral representation, also known as plane wave decomposition. Plane wave, it sounds tautological. With this I think we will have some integral we can estimate asymptotically using fake saddle point. So what I propose to do is to estimate this integral first asymptotically. Of course, when we estimate it asymptotically, we should get a plane wave because it is a plane wave. Okay? Nothing much happened. I just wanted to obtain this expression. Good? Okay. So let's start. First, what I noticed that for psi minus theta bigger than 0, any function, if you remember, exponentially decays for positive arguments and oscillates for negative arguments. So I will discard the bit which corresponds to positive difference of psi minus theta, because then everything decays exponentially and we have no oscillating terms. And for psi minus theta less than 0, we will use asymptotic. I also introduced last time. Approximately. For big Z, this is also approximate. And okay, let's write our integral and then with this form. So then approximately U in is equal writing down the constant, and of course here I will write it as a sum of two exponents, because I want to apply saddle point method. I want the thing to be an exponent. So the form I like is like this. Also, I don't want to write it as sine. I will shift the face and write it as cosine. Yes. I don't like much about this. It doesn't matter, just to make things look a bit neater. So this is the Fourier part, and now it's multiplied by two exponents. So here I have not plus pi over 4, but minus. That's pi. Let's update it. That's it. Okay. To this thing, you know how to apply fixed property. What is our phase function? I'm sorry that there is a lot of algebra today, but that was my intention to make things simple, accessible. Otherwise, I would have just given final results. Things would have looked too complicated, more complicated than they really are. Oh, the first derivative, yes. So, what can we say for that? So this is for this first term, and I'm ignoring the second term. The first term, we can definitely say we have no stationary phase points for tau, for tau less than 0. But for positive tau, no any points. And for tau bigger than 0, we have a certain point. Which should look familiar to you. It's like a straight line with parabolic coordinates. And well, this is kind of upper half of the half plane. But now we have no scatter, so it's just a plain wave propagating. I just made, like what I did, I made a very complicated change of variables, then I made a complicated decomposition, and now I estimated it asymptotically. So, but anyway, I have a plane wave, I will get a plane wave at the end. checking that I'm doing anything right. And then, if we substituted, use the formula I gave you, we will have for upper half plane the following result. Please check the speed algebraically yourself, but you can see it from. At least you can substitute this face and see that that's what you get. So subtract this, but just substitute the face and you will see that that's what you get for the constants also. Okay. We can analyze the second part, and the second part will give us, here we have minus, it will give us a plane wave for tau less than 0. So we obtained as asymptotic representation of the plane wave, a plane wave, which is makes things consistent. So it's like a demonstration that fake saddle point method worked. And this is okay, but I think we can. You can ask your questions if you have questions. And if you don't have questions, we can make a short 5-minute break and continue.
So is it like, so we showed that it works for plane wave, and this is sufficient for us to use it for more complicated
No,
waves?
it's not sufficient. It's just demonstration of the technique. Of course, if you want to be formal, you need to prove it formally, and you need to use a real saddle parameter. But what I'm saying to you, that if you have a saddle parameter, it basically doesn't matter whether you have a big parameter or not. Almost always. But you can I think you can find a change of variables. Then after you do a specific change of variables, you will select a big parameter, because of course for asymptotic, like here I write the first term and then I need to write like big of something. So I just avoiding this part. So I'm not saying what is big and small, but you can find it.